Welcome back to our Chem 152 video series. This video will be covering amphiprotic species and how they can act as both acid or base depending on what you place them with. We'll start this problem with NaH2PO4 plus Na2CO3. Notice that these compounds are both attached to a 1A metal, sodium, so let's first see how they would break apart and what they would leave behind. Now, if Na breaks off from H2PO4, that will give you one piece of Na positive and one piece of H2PO4 negative. Now, H2PO4, we can see, begins with H, so this H2PO4 could be an acid. However, because it is also negative and not on our list of super weak bases that we have in the bottom right corner, it could also be a base. Any compound that could act as both an acid or a base is called amphiprotic. Also bear in mind that sodium plus does not take part in any acid-base reactions at all. We can safely ignore it from here on out. Since H2PO4 negative is amphiprotic, we can't say yet whether it will act as an acid or a base without looking at what it reacts with. So we must also break apart the Na2CO3. If Na2CO3 breaks, it'll break into two pieces of Na plus and one piece of CO3, 2 negative. Just like before, we can safely ignore the Na positive because it will not take part in any acid or base activity. So we're going to concentrate on the CO3 2 negative. We might notice CO3 2 negative does not have any hydrogen. Because it has no hydrogen, there's no way for it to act as an acid. Notice also that it is negative and it is not on the super weak base list. For that reason, the CO3 2 negative will act as a base here. Now, since the CO3 2 negative can only act as a base, that means that it must be the base in this reaction, and H2PO4 minus must be the acid. Therefore, we'll label the H2PO4 as our acid, and we'll label the CO3 2 negative as our base. Now that we know which reactant is acid and which reactant is base, let's think about what happens to an acid or a base during an acid-base reaction. The acid must lose an H and go one step more negative. Bear in mind that we are only losing one H at a time. The base must gain an H and go one step more positive. Again, bearing in mind that we are only going to gain one H. So if H2PO4 loses a hydrogen, it goes from 2 hydrogens down to 1, giving us HPO4. If we were already negative and want to go one step more negative, we are now 2 negative. To that, we'll take our base, CO3 2 negative, and give it an H. This changes the formula to HCO3. We also go one step more positive. If we have 2 negative and we go one step more positive, all that does is reduce our amount of negatives and brings us up to -1. We symbolize that with a simple negative sign above the HCO3. Also remind ourselves that the acid becomes the conjugate base, and remind ourselves that the base becomes the conjugate acid. Therefore, we now have an equation with H2PO4 negative acting as our acid. Now we look at another example with H2PO4, and let's determine whether it will still act as an acid in this case. Once again, we have NaH2PO4, and we will break it. We already know this breaks into Na plus and H2PO4 negative. We also know that the Na plus does not take part in any acid-base activity, and so it's the H2PO4 negative we need to pay attention to. And once again, we don't know yet whether it's an acid or a base, so we look to the second reactant. HClO4 starts with H, but also notice that it is on our list of strong acids that I've written in the bottom right. Because the HClO4 is a strong acid, we can assume it will absolutely act as an acid, and it will never want to act as a base. Therefore, we now know that the HClO4 must be the acid, and because HClO4 must be the acid, the H2PO4 negative must be the base. Now, let's rewrite this. We'll label our base and our acid. Our base must take an H and go one step more positive. Our acid will lose an H and go more negative. Therefore, our H2PO4, if we gain an additional H, that will take us from 2 H's up to 3 H's. And it will take us from a negative up one step to neutral. Because it's neutral, we write no charge in the upper right. Now HClO4 must lose an H, leaving us with ClO4. It also must go one step more negative, giving it a charge of -1. Therefore, H2PO4 negative acts as a base and becomes H3PO4, leaving H3PO4 as our conjugate acid, and meaning ClO4 negative is our conjugate base. So now we've seen an example with NaH2PO4 as a base and an acid, depending on what we place it with. This will be how amphiprotic compounds act. They will act as either bases or acids, depending on what we place them with. Thank you for watching, and we'll see you again soon.